All right, let's try out this problem called count unreachable pairs of nodes in an undirected graph, right? So what does this problem say? Let's have a read. So essentially what this problem says is that it's an undirected graph. The way it's represented or the way it's given to us is there are n nodes, number from 0 to n minus 1, and we are given a 2D array edges which represents all the different edges. Edges of I is AI, BI indicates as an undirected edge between A and B. We have to find the number of pairs of different nodes that are unreachable from each other. Okay, in this example, all nodes are reachable to each other. So the answer is 0, quite clear. In this node, there are sort of three different components as quite clear, right? So there is one component which are all reachable. All nodes within a component is reachable, which is also that's why it's called connected component. So there are three different connected components, one of size 4, one of size 3, and one of size 2. So you could loop through. So if I go back to, let's say, a whiteboard here, and if I go do, so we have three components of sizes 4, 2, and 1, right? So basically choose any two at a time, right? So you can choose 4 and 2, right? There will be 3C2, there will be three different options. So 4 and 2 is one, 4 and 1 is another, and 2 and there are three different options. So here you do take 4C1 and 2C1. Here you do 4C1 and 1C1. Here you do 2C1 times 1C1. So essentially you get 4 times 2, 8, plus 4 plus 2, which is 14. So the problem here is the way to choose any two at a time. You will need a two-way for loop, right? Which like you will loop an outer loop from first to last, and the second guy will start from like I will go from, let's say, 1 to n minus 1, and j will go from I plus 1 to n, sort of, right? Can we avoid this loop here in a different way? So for example, let's maybe try and look at a different example, or rather, yeah, let's take a different example first. Let's say some random example. Let's say we have multiple kind of components, one of size 4, other of size 5, other of size 3, and other of size 2, right? So total nodes are how much? Total nodes are 9 plus 3, 12 plus 2, 14. So there were 14 total nodes, right? So one of the ways now to choose six different components, right? Sorry, two different components will be 4C2, which is 6. Right? So there are six different ways to choose. So you can see one is 4 times 5, one is 4 times 3, one is 4 times 2, right? So for this, we loop from this to this, right? And I would sort of do this. Then 5 times 3 plus 5 times 2 plus 3 times 2, right? So 3 plus 2, 5 plus 1, 6. These are the ways. But you can sort of see, right? This is 4 times 5 plus 3 plus 2, right? Which is what? 5 plus 3, 8 plus 2, 10 plus 5 times 5 plus 3 times 2. Okay, so we're reducing it. So I'm trying to avoid the double loop sort of if we can. And I think we can. So let's understand this, right? So initially, let's just use a different color. So initially, we have nodes. I'll call it remaining nodes, right? So initially we had 14 nodes, and I'll say elements in component, and I'll say unreachable pairs, right? So to begin with, there were 14 elements, and if the first component that I find has size 4, so that means remaining elements now are 10. So there are 4 elements which are in one component, 10 elements that haven't been looked at so far, but these 4 cannot reach these 10, right? So you go essentially 4 times 10, which is 40. All right, next component that you find is of size 5. Now, this 4 have already been processed, so you don't have to. So now only you have to deal with is these 10. within these 10, you find five elements in a single component. That means there are remaining five, right? So that means 5 times 5 is 25. And the third element you find is of size, is it 3 or 2? I don't recall. Maybe 3, right? So if it's 3, that means the remaining is out of these 5, 3 are in one component, 2 we haven't noticed, but these 3 definitely cannot be reached to these 2, right? So 3 times 2, which is 6. And the last component we find is of size 2, that means remaining is 0. So all these two are in the same component. So within these two, there is no remaining, right? That means they're all connected. So plus 0, which is exactly the same as this. And this we sort of do without having multiple loops, right? So we'll try to use this logic. So let's come to the code and try and implement the code for this. All right, so let's see what we have to do. First, let's convert the representation into an adjacency list-based representation. So we take a list of integer, right? And we call it our adjacency list equals to new. Let's say we use an array list for each of the nodes. So I equals to 0, less than n, plus plus. Let's first create an empty adjacency list. So adjacency list dot add a new array list, right? So that's how we get a list of lists. And now let's fill these adjacency lists based on the edges. So let's loop through each edge. So int array edge, each edge in edges. Now adjacency list of cat, edge of 0 is one node. In this we add edge of 1, and it's an undirected graph. So we do other way around as well. Adjacency list of 1 add edge of 0. All right, so now we have an adjacency list based representation. Now what do we want to do? We want to do a DFS to sort of traverse or find all connected components. So let's create a Boolean visited array that will be needed for that. All right, anything else we need? Well, let's define that remaining nodes. And because we have to sort of return a long, let's use long everywhere. To begin with, we haven't done any processing, so start with n. Now we want to do for each node. So I equals to 0, less than n, plus plus. If it's already visited, if it's not visited, then it will be part of a different component, right? So if it's not visited, then it's a different component. All great. So we find the components. So elements in component is what we find. Again, let's make it long instead of int. So elements in component, and for this, let's use a DFS. And what do we pass to this DFS? The adjacency list, visited array, and this I. And now, so out of the remaining nodes, we find these elements, we process these elements, right? So the remaining nodes reduces now. So remaining nodes minus equals to elements in component. And what we are interested in another bit is unreachable pairs, initialize them to 0. So now we have two sets, right? So we have these remaining nodes and we have these elements in component, right? So, and these two add up to these remaining nodes that were initially. So out of these remaining nodes, we process these. So now we are left with these, and these two sets sort of can't be reached. So unreachable pairs plus equals to elements in component times remaining nodes. That's the logic we sort of discussed, and I think that's it. And we return these unreachable pairs. Okay, now let's implement this DFS. Note that in this DFS, we are returning the elements in the component. All right, so we do long a DFS. The three inputs to the DFS are this adjacency list. All right, this visited array, and we have a source node. All right. Again, if this node is already visited, let's handle that case. So if it is, all right, not in, if source is visited, well, the number of elements, that means it's already part of another connected component which has already been processed. So we don't find a new connected component, return 0. Otherwise, we mark it visited. Now we have visited. So, and we initialize elements to 1, at least this node, right? Now, let's see if we can reach more nodes from this node. So for that, let's do a recursive DFS. So for each integer, a neighbor, let's look at all of its neighbors. So for each neighbor in the adjacency list of source, let's do a DFS. Rather, let's find what that returns and add elements to that component, right? So DFS, adjacency lists, visited, and neighbor. That's it. And then we return total elements. So that's our entire logic. Let's run the code. Okay, let's see what compilation error we get and fix that. Missing a bracket. Run again. Okay, I think there's an extra bracket here. Let's fix that. All right, the two test cases pass. Let's submit to see if all test cases pass. And it does. All right, so that's good enough.